Now we start today a very important aspect, that is basically the segment and offset concept, or in other words the segmented memory concept that is used by the Intel family of microprocessors. By segmented approach we mean that each address of the 8086 or in general Intel compatible processors is generated by having addresses 16-bit address from the segment register followed by a 16-bit address from the offset register. So we can write that we can have a 20-bit physical address, and that would be formed by using the segment address will multiply by 10h, and then we add the offset address to it. So this is the generic formula. If we want to find the 20-bit physical address for any location, we'll take the segment address, we'll multiply it by 10h, and then we'll add the offset address. Now, so there are four registers, four segment registers, the CS code segment, DS data segment, ES extra segment, and SS stack segment register. And of course, like I discussed previously briefly, every segment address would have the offset address, right? So if we are talking about CS, we have got the IP, which is the offset address. If we are talking about the DS, it is the SI. And if we are talking about the ES, it is the DI. And if it is the stack segment register, it is the SP or the stack pointer register. So let's first talk about the CS of the code segment register. Define the starting address of the section of the memory holding the code. So the segment address is basically telling you about the starting address. So if you want to find the starting address of the code segment, we look at the CS register. If you want to look at the starting address of the data segment, we look at the DS register. Similarly for ES and similarly for SS. So in real mode of operation, which is precisely what we are studying at this moment, it specifies the starting address of the 64K code segment. Similar is the discussion for the DS. Nothing has changed, but DS is telling you the starting address of the data segment, the place where data is kept. Similarly, extra segment register tells us about the starting address of the section memory holding the extra data, or EST. So of course we are specifying again the starting address of the segment. The segment size is 64K. This is an important point that we'll be looking at later on. Similar discussion can be followed for the stack segment register, which is telling the starting address of the 64K stack segments, and so on and so forth. So again, some discussion about segments as offset. Segment address is the starting segment address of a segment, right? So let's say if we have a memory map, right? Let's say this is a section of memory we are looking at. This is the start of the segment, right? So this starting address would be given by the segment register. If we are talking about the code, we look at the CS. If we are talking about the data, we will look at the DS. Similarly, for the extra data, we look at ES, and for the stack segment, we look at the SS register. So the segment register tells us the starting address of the segment, and any particular location in this particular segment can be given by the offset address. And like I discussed before, if you want to find the physical address of this location, which is 20 bits, we'll take this segment address, we'll multiply it by 10h, and then we'll add this offset address to get the 20-bit physical address of this particular location. So offset address selects any address in that segment. Again, this is some roundup of the hex, right? Hex digits that we can use in these calculations. Now let's look at a little quick roundup about hexadecimal numbers. If we are converting from binary to hex, it is very easy. We'll make groups of 4 binary bits and we'll write the hex code for each. So 1111 is F, 0010 is 2 and 0001 is 1. So this pattern in binary is equivalent to this in hex. As far as hex addition is concerned, we can do it directly. For example, this is the first hex digit, this is the second hex number, and this multiplication is taking place. So if we want to calculate F plus D, we know F is 15 and D is 13. So F plus D comes out to be 15 plus 13, which is 28. Now since 28 is greater than 16, which is the highest number or base of hex, we'll divide 28 by 16. So we divide 28 by 16 to get the remainder of 12. Now 12 is hex digit C. So we write C over here and we carry 1. Again 9, 10, 11, 12 and this is now 13. So 13 is which hex digit? 13 is D. So we write D over here. This is 7 and this is 2. So 123F plus 159D comes out to be 27DC. Now this is again an elaboration of segments and offset. So this is how basically what we can carry out, right? Let's look at an example. The segment register over here contains 1000. Let's say this segment register is CS for consideration. Now this segment register can be any segment we are talking about. It can be DS for data segment, ES, and the concept will remain the same for this kind of things. Okay, so this is a CS. If CS contains 1000H, so what would be the physical address of the start of the segment, right? So for the physical address of the start of the segment, we'll multiply the segment address by 10H and then we'll add the offset. Now for the starting address, the offset is 0. So what would be the segment physical address? It would be 1000 into 10H, 1000 into 10H. Now when we are multiplying any hex value by 10H, the simple idea is to just add a 0. So it would be, 10,000. So for the first location of the segment, the offset address is all 0, or offset is 0000 hex, right? Because it's a 16-bit offset. So if we are talking about the CS, we can call it IP. So let's say this IP is 0000 for the first address and the segment physical address is 10. So what is the physical address of the start of the segment? It is CS into 10H, which is 10,000H, plus 0000H, which again comes out to be 10,000H. So 10,000H is the physical address of the start of this particular segment. Now let's say if the offset is F0000, so what would the physical address of this particular location? Again we'll do CS into 10H, which would give us a value of 10,000H. And then we'll add the offset, which is F000. F000. So after a very difficult calculation, we get 1F000 hex. Now this is the physical address of this particular offset location, which is this. Now last but not the least, we said that each segment is 64K, right? So why we are saying that each segment is 64K? Very easily we can verify, right? Let me clear this discussion. Now again we talk about the CS, which is an example is sending the 1000H, right? So CS into 10H we know. Comes out to be 10,000H. Okay. Now if I want to find the length of this particular segment, I would look at the last location of this particular segment. So what would be the offset of last location? Offset of last location should be the highest value of the offset register. So if we are talking about IP as the offset register, what would be the highest value of the register? It would be F, 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 F. So quickly we can find out the physical address of the last location of this segment, which would be 10,000H plus FFFFH, which comes out to be 1 F, 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 X. So now this is the last location. And what was the physical address of the first location? 10,000H. So one of the ways of finding the length of this particular segment, the total number of locations in it, is to subtract the first location physical address from the last location physical address, which comes out to be F, 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 right? So this value comes out to be 64K. So hence we say that the length of each segment is 64K because each offset register is 16 bits. If you would increase the size of the offset register, then the length of this segment would also increase. And this is in fact some of the approach that is taken by Intel.